Okay. They have dropped message that you should be ready with pen, paper, that is your notebook and calculator. Hope everybody might have calculator with them and you are able to solve the problem. See, when we are going to see that problem, because we have started this problem for last lecture and we have completed it up to its need only, where we have completed the design of pins. That problem was related to the bell crank lever, which has connected to load W. And also in this problem, that the length of that bell crank lever has given, and its the length and its allowable tensile stress and allowable shear stress is also given. Then the safe bearing pressure that has given, that bearing pressure is related to the pressure which that pin can sustain. So we have seen that in this bell crank lever, we have designed the pins at three locations where we have designed that pin for, or we have just started that design from pin at point F, that is fulcrum, and then afterwards we have taken the same pin which we have designed at point A, the pin which we can fix here, and later on we have seen that pin which we can fix at point B. And all these pins which we have designed are designed for bearing pressure first of all, that is stress which may get induced because of the bearing, pressure which has generated on that pin, and later on we have checked it for the double shear because these pins are undergoing for the double shear. So these three pins we have designed, and then afterwards we are about to design this lever. So first of all we have calculated this W, P, by using this W. Later on we have calculated the reactions at fulcrum, this RF, and then afterwards we have designed the fulcrum pin, that considering the D as a diameter and L as a length of this fulcrum pin, and by equating the bearing pressure and the force which is acting on this pin, and that force is naturally the reaction which is coming at the fulcrum. And then we have checked it by means of shear stress, double shear, and we found that this double shearing stress is 7.7 megapascal, which is well below than this 60 megapascal. And later on, we have designed the bush inside that uh, lever and above the pin. The thickness of this bush we have considered as a 3 millimeter, and that's why we have calculated the diameter, which we are going to elaborate for the lever, and that diameter we have calculated as a 42 millimeter. Okay, and by considering the 3 uh, millimeter thickness of that bush, uh, that bush diameter we have calculated as a 42 millimeter, and 72 millimeter is the diameter which we have calculated for the increase the thickness of that lever. Then afterwards we have checked that bearing bending stresses in the pin, or we were about to calculate the bending stress. Where we were last time? Hello? Can anybody answer me? Hello?
Yes, sir.
Abhinay Gaikwad. Okay. Harshvardhan. We have designed it, right?
Sir, yes, sir. The design of pin at B, sir. In the last lecture
Huh.
we have covered.
We have covered at design at point B. Okay, so let me cover this part also, that design at point pin design of pin at point A. As the A and F points are not deferred by means of load, only a load which we have considered at point A or which we have calculated is 15,000 Newton, whereas the load which we have calculated at point F is 15,660 Newton. Only difference is of 660 Newton. That's why we have considered same dimensions of the pin at point A also. So this you have to mention, if you are going to solve this problem, then you have to mention this statement that the effort at point A is 15,000 Newton and fulcrum reaction is 15,660 Newton, which is not much more different. That's why we are going to use the same pin and are also less than the fulcrum reaction. The efforts which we have applied are less than the fulcrum reaction. That's why we can use the same pin or same dimensions of the pin at point A. Then we have considered the dimensions of the pin at point B and D1 because it is different diameter, because the load which is coming on at point B is only 4,500 Newton, which is very much less than the 15,000 Newton. So definitely we are not going to use the same sort of pin, as you have only given answer that it is a wastage of material and unnecessarily cost will get increased. And that's why using the same criteria of bearing pressure, we have calculated the diameter of that pin, also the length of that pin. In this, we have assumed that length of pin is 1.25 times than the diameter of pin. So by considering that, we have calculated diameter of pin D1 as a 20 millimeter and length of pin as a 25 millimeter. After that, the bush which we are going to use, that we will see later on. But by considering the double shearing of that pin, we have calculated the stress which will get induced, that is shear stress, and that is 7.16 megapascal, which is very less than this 60 megapascal, which is the allowable bearing shear stress. So we have taken the same dimensions for the pin, which we have calculated as 20 millimeter diameter and 25 millimeter length. And we were at this point where we have we have to calculate or we have to check the bending stresses which are coming. Okay, and also we were calculating the bending moment. Okay, so here is the bush which we have calculated, dimensions of the bush for the pin which is at point B, and that is equal to, here we have considered the thickness of that bush as a 3 millimeter, as we have seen in case of bush which we have designed at point F. But you can change this thickness. You can consider it as a 2 millimeter thickness, because the load which is coming is comparatively very low, and that's why it can be 2 millimeter. But here we have chosen as the same bush, okay, of 3 millimeter thickness. So the outer diameter of that bush will become 26 millimeter, that is diameter of pin plus 2 into diameter of thickness of that bush, that is 6. So 26 millimeter is the diameter of that bush, outer diameter of that bush, and outside diameter of that eye, that is nothing but the thickness which we are going to increase by means of 3 millimeter of that lever. That diameter is nothing but the diameter of pin multiplied by 2, and that is coming as a 40 millimeter. That's why if you are going to see the diagram, this outer circle diameter is 40 millimeter. Here, this outer circle diameter which we have calculated is the equal to diameter of this pin multiplied by 2. Here also the outer circle diameter, that diameter is 2 times the diameter of the pin which we have designed at point A. Likewise, we have calculated the dimensions of that bush at point B. Now we are going to take the bending into account. So what we are going to do is that we are going to calculate, since the B end is fork end, okay, and therefore thickness of the each eye, we have calculated that thickness of that fork end as a T1, and that is equal to L by 2, that is length by 2. That same sort of forks we can design at fulcrum as well as at point A also, where the effort is applied. At point A, same sort of fulcrum will be there. At point F, same sort of fulcrum will be there. And at point B also, same sort of fulcrum will be there. Okay. That if you want, I will draw here the fulcrum drawing also. Fulcrums will be of this type. And this we are going to, in between this double eye section or fork, we are going to insert that pin. So this pin will be which we are going to insert here. Okay, this color will change, and that's why it will become a case like we have seen in case of knuckle joint. Here we are going to insert the pin. Okay, so dimension of pin will be different. So let it be. Now we are going to see how we are going to calculate the bending moment. I think all of you know already that how to calculate the bending moment if this is the shear force diagram. Okay, then how you are going to calculate? How you are going to calculate the bending moment at point where this point already I think we have given name to this point. Is it right? O is the name. So we are going to take the bending moment at center, YY section. Okay, and O is the point where we are going to calculate the bending moment. So when we are going to calculate the bending moment at this point, which we are going to call as O. So from one side only we are going to calculate the bending moment. There will be same case for the other side. Okay. So we have considered the load which is acting, that is W by 2, which is acting in downward direction. Okay. Which is nothing but the load which is coming at this point. Okay. So this W is the load which is coming at point B, and reaction which is not naturally, if the W load which is acting in downward direction, there will be two reactions in upward direction. Here the reaction will be one reaction, and here the other reaction will be. And definitely that reaction will be, is it visible? Anybody have?
Yes, sir.
Okay. Now this is the reaction. These are the reactions which are coming as naturally that W is acting in downward direction. At center we are going to consider, though it is uniformly distributed. But while we are going to calculate the reaction, at that time we are going to consider it as a point load. W which is acting. So W by 2 will be the reaction which is coming. Okay, this side, and W by 2 will be to the other side. At this side, which has been mentioned here. So when we are going to calculate the bending moment, at that time, is bending moment. For that, we have considered the W by 2 load which is acting in downward direction. Okay, and one more load, that is W by 2, which is acting in upward direction, and that we can consider here, that W by 2 which is acting in upward direction. Okay, so this W by 2, what will be the distance of this reaction W by 2? I want to calculate distance. So if you want to find out the distance of this point from O point, what will it be that distance? Can anybody of you tell this distance?
Yes, sir.
So how much it is?
Sir, it is L1 by 2 plus T1 by 3.
L1 by 2 plus T1 by 3. Anybody else want to add it? It is L1 by 2, that is this distance, plus this T1 by 3. Am I right? Yes. Is it? It is L1 by 2 plus T1 by 3. Okay, we have calculated this distance, and which is correct one. From diagram it can be seen it is correct. Okay, so what will be the bending moment now at point O? What will be the bending moment? Who can tell me? Sarvade, in which direction it will be? Bending moment which has created because of load W by 2, which is acting in downward direction. How much it will be? Hello?
W by 2 into L1 by 4, sir.
W by 2 into L1 by 4, right? So when we are going to say this bending moment, that will be in anti-clockwise direction. Am I right? The arrow is showing that
Yes,
bending
sir.
moment. Yes. And bending moment which is created by W by 2 at L1 by 2 plus T1 by 3 distance, that is going to create movement in which is upward direction. Am I right? And that you are going to call as a
Clockwise.
clockwise direction. So this is not going to show us clockwise direction. Look at it. It has to be no, it is not showing clockwise. This is anti-clockwise only. So we cannot use this. So anti-clockwise direction. Yes. This bending moment will be created in anti-clockwise direction. So what will be the total bending moment at point O? Because of the W by 2 at L1 by 4 and W by 2 at L1 by 2 plus T1 by 3. Yes, you can write it on your
W by 2
notebook.
into L1.
W by 2 into, hello?
L1 by 2 plus T1 by 3 minus
Huh?
W by 2 into
Huh?
L by 4.
L1 by 4. Okay. This will be the bending moment at point O, which you can see on this slide. Right? So this bending moment, just we are going to simplify this equation, and this minus sign, and here it is plus sign. So we are going to put the value of W also. W is here. So we are going to just simplify it. Okay. And that will be 5 by 24 W into L1, where we are going to consider the thickness, because already we have calculated this T1 value, and that T1 value is L1 by 2, which is 12.5 millimeter. Later on, we will put the value that is 12.5 millimeter. But here we are going to just mention this T1 is equal to L1 by 2. So in this equation, if you are going to put the value of T1 also, this T1 value in form of L1, this total equation for the bending moment will become 5 by 24. How it has come as a 5 by 24? Because this for 8, and this we have to again make as a here L1 by 2, it will become 6. So this 6 will be common, and 6 multiplied by 2 is 12. Okay. So just we are going to take the common denominator, and that will be 24, because here it is 8 and here it is 6. And we are going to add, that is subtract actually, and we are going to get this value as a 5 by 24 W into L1. Okay. So W, which we have calculated already, or which is given in the problem actually, is 4,500 Newton. L1, which we have calculated, that is 25. So the bending moment, which is coming as 23,438 Newton per Newton millimeter. Now here I have written directly the answer, that is sigma b. But how this sigma b is coming? So we are going to use the equation as, what is the equation for calculating bending stresses from bending moment? Can anybody tell me that equation?
M by I is equal to sigma upon Y, sir.
Yes, M by I is equal to sigma upon Y. So I, which I you are going to consider, is equal to sigma upon Y. M divided by I is equal to sigma B upon Y. This sigma B upon Y. So which section you are going to consider for the taking this I? Are you getting my question? Hello? From which we can calculate the sigma B. So what will be the value of I? It will be cubed by 12 or pi by 64 d raised to 4. Which value you have to take? We are calculating bending moment for what? Is it for fork? Is it for that uh, arm, or is it for pin? I'll repeat. बेंडिंग मुवमेंट आपण कशाची काढले? पिनची काढले, फोर्कची काढले का लिव्हरची काढले? परत एकदा बघा त्या डायग्राम मध्ये. हॅलो, कुणीतरी एकानं उत्तर दे की. ही बेंडिंग मोमेंट जी कॅल्क्युलेट केली ती फोर्कची कॅल्क्युलेट केली का ह्या पिनची केली फोर्कची केली का
पिन सर.
पिनची बेंडिंग मोमेंट कॅल्क्युलेट केली आपण ड्रॉ केली बरोबर आहे ही बेंडिंग मोमेंट जी कॅल्क्युलेट केलेली आहे ती पिन साठी केली पिनवर लोड ऍक्ट होतोय पिनच्या रिएक्शन आहे त्या ओके सो विच आय वी हॅव टू कन्सिडर दॅट इज मोमेंट ऑफ इनर्शिया कशाचा मोमेंट ऑफ इनर्शिया घ्यायला पाहिजे आपल्याला
पिनचा सर
पिनचा किती आहे तो
पिन सर.
पिनचा बरोबर आहे किती आहे तो हा
सर
पिनचा बेंडिंग
560 into d raised
काय I is equal to 5/64 d raised to 4 बरोबर आहे ना क्लासमध्ये आहेत का सगळे हॅलो
yes sir
हा काय बेंडिंग मोमेंट आहे त्याचा d1 here we have to consider d1 raised to 4 and what will be the y
d by 2 sir d1 by 2
d1 by 2 y will be d1 by 2 then put values and calculate sigma d first of all you tell me what will the z I have written what is this z what
section modulus
section modulus how the section modulus is calculated
I by y sir.
I by y right so calculate the section modulus first for pin the z is section modulus and is calculated as moment of inertia divided by y. So calculate section modulus. What is the section? What will be the section modulus for this pin diameter d1? It will be I divided by z. Have you calculated it? What value you are getting? Hello? Do you have a calculator with you? Nana Sahib Shinde. Hello? Nana Sahib Shinde. Rupesh Dehre. Nana Shinde, you can text a message. What is the value of Z? Section modulus.
sir 2 sigma
हा विद्यार्थी किती काय म्हणताय Yeah, sir has calculated it as a 785.39.
Yes sir, 785.39.
Yes, and it is approximated to 786. Okay, so that is the section modulus for the approximation means it is not required to have the approximation, but we have taken the whole value as a 786. Okay, 786. So m which we have calculated that is 23,438 divided by 700 86, and we are going to get the value of sigma b, that is bending stress, equal to 29.8 megapascal. And what value of allowable bending stress is given in the problem? What value of allowable bending stress has given in the problem?
10.
Pardon? It is bearing pressure, 10.
Okay.
If you want to see problem statement, once again we'll go to the problem statement. See here, shape tensile stress is 75 megapascal. What will be the bending stress then? Shape bending stress. Hello? What will be the value?
75, sir.
75 only, which is equal to, because in any problem this bending stress will not be given separately. That we have to consider as a tensile stress only. That is, the value of bending stress is equal to tensile stress. Okay, because in case of bending, again and again I am repeating that in case of bending, the tensile and compressive both stresses are coming, and out of that we are going to consider that bending stress as a tensile stress. Okay, so while bending is occurring, that where we can have the bending is this. So in case of bending stress, we are going to get the value as a tensile stress, and we have the allowable value of bending stress, that is tensile stress, is 75 megapascal, and which we have calculated is 29.8 megapascal. So definitely the values which we have calculated for the dimension of that pin are safe, and hence it is working in bending stress also. So all three pins we have calculated dimensions. Now we have to just calculate dimension of lever. Now for the lever, we are going to consider that T as a thickness and B as a width of that lever. Okay. So when we are going to consider that thickness of lever and width of that lever, then just we are going to calculate the center distance from the fulcrum. Okay, that is YY section which we have taken as 50 millimeter. Therefore, the maximum bending moment will be at the center. Now, just I will copy this image, first image of that lever, this image, and we'll put here. Okay, this is lever where we are going to get, later on I will delete it, where we are going to get the maximum bending, and that we are going to get at this point. Am I right? Hello, is it right? Anybody of you? Because this W is acting here, and we are going to get bending moment at this point actually, where the section is most weak. And just we have to calculate this distance, that is distance from this black point to the center of this B. So can you calculate this distance? How much it will be? I'll repeat. I want this distance. How much this distance will be? Anybody of you? Is it 500 millimeter? That black point to point B distance, whether it will be 500 millimeter.
No, sir. Less than
No, sir.
500.
Less than 500. How much we have to less? Is it equal to half of the diameter which we have calculated at point F? Diameter
Yes,
of
sir.
pin which we have calculated at point F. So what diameter of pin which we have calculated at point F? Diameter of pin at point F which we have calculated is equal to 36 millimeter.
36. Yes.
36.
Right, 36 millimeter. So just we have to subtract 36 by 2 from 500 millimeter, and at that point we have to calculate the bending moment. Am I right? So the bending
Yes, sir.
moment which we have, yes. So bending moment which we have calculated is W multiplied by distance. That is 4,500 multiplied by distance is 500 divided minus 50, and that will be 2025 into 10 raised to 3. Are you getting? Now just we have to calculate, as somebody has told, that section modulus, because here also we are going to use the same formula for calculating bending stress, and that formula is the replica of the formula which just now we have derived, this formula. So here we can use this formula. Now you are not able to view this formula. So is it visible now? M by I is equal to sigma B by Y. Only thing is that this I will get replaced, and this I will be how much? BD cube by 12. Am I right? Hello?
Yes, sir.
Because the section which we are going to consider for the lever is rectangular section, which has width equal to B and thickness equal to T. So this B T cube by 12, because if you are going to see the diagram, see this B is the depth and T is the thickness, which already we have considered. So this I will become BD cube by 12 instead of this 5 by 4, 5 by 64 D raised to 4. So here I have to write this T B raised to 4 BD cube by 12, BD cube by 12. Okay, and Y will be, how much Y will be? T by 2. So section modulus which we are going to calculate is I by Y. So what value of section modulus you are getting now? Just put T B value and take this I by Y. What value of section modulus you are getting? Hello? Are you calculating it? कौन calculate करता है क्या? Hello? Section modulus will be 1 by 6 into T B square. If you are going to put the values of this T, that is Y equal to T by 2, I equal to T B cube by 12 in this equation of section modulus Z, then you are going to get this Z is equal to 1 by 6 into T B square. Okay. Now from standard design data book, already we know that normally the thickness is not actually the depth of that lever is considered equal to 3 times the thickness. Okay. This already we have seen in the table which we have seen when we are going to use rectangular cross section, when we are going to use that elliptical cross section, what are the ratios of that thickness and that depth. So we are going to assume that B is equal to 3T, and if you are going to put this value of B equal to 3T, it will become 1 by 6 into T into 3T square, and it is coming as a 1.5 T cube. So this T cube we are going to consider, and we are going to use equation as this bending moment, that is sigma B is equal to M by Z. Now we know that bending stress which is allowed for that material, and that is equal to 75 megapascal, and that is equal to 75 into 10 raised to 75 Newton per millimeter square. So this 70 sigma B is equal to M by Z. M which we have calculated, which is equal to 2025 into 10 raised to 3 Newton meter, that we have written here, and value of Z which we have calculated as 1.5 T cube. So we are going to get this 75 is equal to 1350 into 10 raised to 3 divided by T cube. From this we can calculate value of T cube by taking this T cube to the other side, and this 1350 into 10 raised to 3 divided by 75, which we are going to get as a 18 into 10 raised to 3. If you are going to take the cube root of this 18 into 10 raised to 3, we are going to get T as a 26 millimeter. Now I need what is the exact value of T. This 26 millimeter is approximated. Can you calculate? Hello? So
Sir,
use your
26.2.
26.2.
2.
Is it above the 26? Then the value which I have mentioned here, is it correct? Should I take it as a 26 millimeter? Hello? Can I take it as a 26 millimeter? What I should
Sir,
write?
26.2, sir.
26.2. If it is coming as a 26.2, it should be 27 millimeter,
27.
right? So instead of considering this 26 millimeter, it should be 27 millimeter. It should be approximated more than that. Anybody else? अजून कोणी कॅल्क्युलेट केले का? हा,
व्हॅल्यू येते सर 26.209.
2089. ओके, म्हणजे आपण 26 कन्सिडर करू शकतो का? ती बेसिक क्वेश्चन.
नाही सर.
नाही, मग ही कॅल्क्युलेशन wrong, right? What will be the value of T is 27 millimeter, and hence value of B, which is equal to 3 times of that T. What will be the value of B? Calculate करा आणि सांगा मला.
81.
किती येते? हॅलो?
81.
81 millimeter. So 81 millimeter is the depth of that lever which we have considered here. Okay, and here we have completed this problem. Now let me ask question that do you have any problem? Who has not understood anything and who has some question related to that? Yes? क्वेश्चन आहे का? ते लिहून
हॅलो सर.
हा हा बोला ना.
मॅक्झिमम बेंडिंग मोमेंट कशी घेतली तेवढं एकदा सांगा.
बेंडिंग मुवमेंट कितली? ओके.
हा सर.
येस, बेंडिंग मुवमेंट आपण जे घेतोय ना ती ह्या पिनच्या शेवटच्या एंडला पेरीफेरीवर घ्यायला पाहिजे. का? कारण जर आपण इथं सेंटरला घेतली ह्या सेंटरला जर घेतली आपण इथं तर काय होईल की हा पिनचा जो भाग आहे तो पण ह्या लिव्हर मध्ये कन्सिडर केला जाईल आणि हा पिन जो आहे इथं तर आपल्याला वीकर सेक्शन भेटणार नाही. इथं कुठं पेरीफेरीवरच भेटणार कारण आपण होल पाडले कशावर? त्या लिव्हरवर. ओके, मग त्याची जी बेंडिंग मुवमेंट जास्तीत जास्त येणार आहे ती या पॉइंटवर येणार आहे म्हणजे टँजंट टू द पिन डायमीटर. ओके, ठीक आहे. त्या ठिकाणी मी ब्लॅक पॉइंट काढलाय तिथं. मग ही बेंडिंग मुवमेंट आहे डब्ल्यू ऍक्टिंग इन डाउनवर्ड डिरेक्शन. डब्ल्यू डाउनवर्ड डिरेक्शन मध्ये ऍक्ट होतोय. सो बेंडिंग मुवमेंट अशी होईल which we are going to calculate at this point. Okay, can I name this point as a x? x पॉइंट कुठला आहे समजले?
येस सर.
हा, आता त्या एक्स पॉइंटच्या भोवती जर डब्ल्यू ने तयार केलेली बेंडिंग मुवमेंट काढायची आहे मला. ओके, तर डब्ल्यू मल्टिप्लाइड बाय हे डिस्टन्स. आता हे डिस्टन्स जे आहे ते 50 मिलीमीटर काय फरक पडणार आहे असं म्हणू शकतो आपण. 500 मध्ये 50 काही जास्त नाही, अप्रॉक्सिमेशन करू शकतो. पण आपल्याला पिनचं डायमीटर माहितच आहे ना. ओके, त्यामुळे आपण तेवढं पिनचं डायमीटर त्यातनं वजा करू, डायमीटर डिवाइड बाय 2. त्यामुळे आपण 500 मायनस 50 दॅट इज द डायमीटर ऑफ दॅट पिन डिवाइड बाय 2 हे घेतलं. ती 500 मायनस 15 ते लेंथ आली आणि लोड आहे तो डब्ल्यू आहे, त्यामुळे आली बेंडिंग मोमेंट.
सर डायमीटर 36 होती सर.
कशाचा?
पिनची सर.
पिनचा डायमीटर. आणि जो बाहेरचा काढलाय तो हॅलो ठीक आहे. मग 36 डिवाइड बाय 2 त्यातनं वजा केलं पाहिजे. हॅलो, हॅलो,
येस सर.
हाँ 36 you minus 36 and calculate the length. 36 divided by 2. परत करा कॅल्क्युलेशन सगळे मग. व्हेरी गुड. आणि बेंडिंग मोमेंट किती येतोय सांगा? Instead of 50 it will be
18 सर.
किती? 8
18
हाँ 18. So 500 minus 18 multiplied by 4500. Instead of this 15, 50 we are going to take as a 18.
2169 into 10 raised to 3, sir.
2169 into 10 raised to 3. Okay. You take this bending moment and calculate the thickness again by considering the same Z. Z is equal to 1.5 into T cube. This bending moment will be what value you have calculated right now? आपण इथे सांगितले किती आले ते?
2169
Just a minute.
into 10
2169
into 10 raised to 3.
10 raised to 3. I'll replace it. M by Z is equal to this value. Okay. Divided by 1.5 into T cube. What value of T you are getting now?
26.8.
26.8. The value of T you are getting as a 26.8 and we can approximate it to the 27. बरोबर आहे?
Yes, sir.
ठीक आहे, आपल्याला 27 मिळाले आणि बी पण तेवढं मिळालं. Any problem?
No,
Hello?
sir.
No, sir.
Okay. समजलं गणित सगळं? Any question? Hello? Can I take present now?
Yes, sir.
So I'm taking present key and roll number 50 is present. 54. Number 1. 5. 6, 7. 10. 13. 16. 17. 31. 33. 34. 37. 41. 47. 55. 58. 61. 70. 77 and 78. Anybody else remaining?
Hello, sir. 44.
Just a minute.